Thank you for coming all to my presentation. I hope you enjoy it. So today we are going to talk about how can we interact with industrial devices. Let me just, yeah. With industrial devices using the Elixir ecosystem, we are going to talk about industrial protocols, communication protocols. But first, let me introduce myself. My name is Aldebaran Alonso. I'm an embedded systems engineer at Valiot, which is a software company focused on Industry 4.0. Our objective is to maximize or optimize the production process of manufacturing companies by using AI with IIoT or Industrial Internet of Things. My main job there is to develop and maintain the device that is right on the corner, that we call it Edge. It's a nerve-based device, and we use it to post data from our real-time sensors to parse the data, execute controllers, and gathering data from industrial devices that are already deployed in our customers' environment. And these type of devices are like PLCs, SCADA systems, motor drivers. So this final concept is the one that we are going to focus on for this talk. This is the content that I would like to cover and share with you, which is talk about the problem, which is how can we connect to these devices, which they don't talk the same way that we used to. This is a common problem from startups and makers that wants to create a product with an industrial environment. So how can we interact with these devices and to collaborate and maximize the value of our product? We will do a brief introduction to industrial communication protocols, as well as we will discuss their features, their constraints, and we will talk about how we had added support to that kind of protocols. We will focus a lot on Modbus TCP and OPC UA. With a little demo, we will grab both of them, and I program it in a Raspberry Pi, so I can share with you how is the interaction by using these kind of protocols. Finally, we will talk about available options for more industrial protocols that are already on open source projects, and we will talk the future work that we are eager to do. So, well, a little disclaimer here. These kind of devices are really we need to be very cautious when accessing or programming industrial devices, since they control many kinds of equipments, and loss of property, production, or even life may be possible by doing so. So always be responsible by doing this kind of operation with this kind of device. Yeah. Now we were going to talk a little bit for the problem. Let's imagine that we are developing a product. This product will be a sensor that measures some variable like temperature, humidity, or even radioactivity, or whatever you can imagine. So we already, let's do the supposing event that we already walk all the way from the concepts ideas, and now we are in the requirement definitions. So we have these requirements. We need hardware to interact with the physical variables. We also need a user interface to configure our device, to calibrate. This is because not all our customers will have the same environment, so it is wise to add this kind of interface. We also need a way to store historical data to analyze the logs, the alerts, the events, and maybe some machine learning to do some signal processing, pattern recognition, or even edge computing. Fortunately, for those requirements, we have the Elixir ecosystem, which help us with most of them. We got nerfs for a robust embedded Linux operating system. We have nerfs hub for OTA updates, over-the-air updates. We have also awesome debugging capabilities such as SSH. We could remote log in the device and see what is going on in real time. We also can help us by using Phoenix to create our web application that will be hosted on our device. We could also use Scenic to create a more physical approach with a touchscreen or something like that. We could use Ecto to store the data with the related packages such as SQLite and store the data right in our local device. And finally, but not least, we could use NX and Action to cover all the requirements on machine learning. So, merging these whole frameworks, we could get something really, really nice of it. We could have a flux capacitor, let's say, which will be a new device that we need to incorporate to our client. So what's the next step? The next step should be to sell it. Well, basically, obviously, we need to test it to make some certification and all that thing that we will suppose we already done. But well, let's imagine that we have to sell it, and the first question that they will ask us is, how can I take your device and integrate with my whole machinery? Well, that's the problem. And not only that, the machinery that our customers will have looks something like this, which are huge and enormous and intimidating machines, which cost millions of dollars, and they don't talk the same way that the same protocols that we know. So, however, we can do a little zoom in this area, which generally this kind of machines has control systems in a room full of cabinets with electronic controllers. If we open one of these cabinets, almost for sure there will be a PLC, which is an industrial computer focused on manufacturing process. They are focused on a robust operating system. They also do a lot of self-diagnostic. But the problem here is that usually this kind of devices doesn't support common communication protocols such as HTTP or MQTT or even WebSockets. They don't talk the way that we used to. So for this, they usually use industrial communication protocol for safe real-time transferring data. So that's the next topic in industrial protocols. Here I show in this slide the SIM pyramid, which is which describes the interaction between layers of the production data, how they are interacting, and the devices that are related to. The most important thing about this slide is the highlighted area which our device is going to fit on, and also I want to point on the arrows that are right there. They show how this parameter will grow depending on the layer that we are looking on. For example, at the base, the frequency is very high with a less data size because a sensor only needs to report like a variable, which is a float or double, and they need to do it quickly enough to make sure that controller has the right context to make that decision and do it in a right way. So this next slide exposes similar ideas, but there are tons of protocols with different comparison between functionality, cost, and frequency and data size. So the reason of how we are going to choose a protocol is highly dependent on the application and our customer what already has deployed in their scenario. And this is the next topic, how to add support to another industrial protocol. So there are three ways that we are going to talk in this talk. The first one is the full Elixir implementation. This is recommended when the protocol is quite simple and it's an open specification, so you can grab the PDF and look how the protocol works, and if it is simple, you could write your own backend for that. We will talk particularly Modbus. Modbus has different types of layers which can transmit the data. One of it is serial with Modbus RTU, and the other one is for network communication, which uses Ethernet and Wi-Fi. So, fortunately, well, I need to explain a little bit of Modbus. It's an old protocol. It was developed like 1979 by Modicon to communicate electronic devices. But in order to support this protocol, we have already some work that we can start with. For example, we have VintageNet to handle the physical interfaces, which is the Ethernet, the Wi-Fi. We also have the GIN TCP library from ODP to handle the transport layer. We also have the Elixir circuits which has a behavior called framing that lets you handle the serial frame in a flexible way to handle the errors and do these kind of things. So we could merge or mix these packages, and we create this library which is called Modbus. This library is for the support of serial and network Modbus communication. We implement both behaviors, the master-slave, which is the communication in a bus, in a serial communication. And Modbus TCP, they use client and server behavior. There is the link that you could access anytime. It's an open source project. And yeah, Modbus is great, but as I said before, it is old. It is an open specification, really easy to implement and understand. Does not require hardware constraints. It is widely used for many devices, many legacy devices and newer devices for compatibility issues. But it lacks of security by default. There is no SSL, there is no TLS, so anyone that is connected to the network or the bus could hear and understand any message that is passing in it. And then the other thing that I would like to share is the modeling of a device with this protocol is quite annoying, because you have to create like a memory address map to expose the data that you are generating. And this protocol only uses two data types, which is Boolean and integer. So if you want to write a float, you have to do it manually. So it's kind of a nightmare if you have a full complete device. So what happens if the protocol has a lot of more features, or maybe it is not an open specification, or maybe the open specification is like thousands of pages to read? Well, for that case, we recommend to look for an open source project that already has that support and use it as a starting point. And how to take that open source project and bring it to Elixir? Well, there are several approaches. One of this is the NIF approach, which we don't recommend because it seems risky, because if a NIF fails, it might crash the Erlang VM. So probably it's not this is not acceptable for the industrial communication in industrial environment. So the safer way to do this, as we know, is Elixir ports. In this approach, you have to create an Elixir process that is communicating to the library that you are intending to use. This middleware will understand the messages for Elixir, and they will call the functions that you are expecting to run. So in this case, you also use Elixir ports. It's a behavior that will be the channel, the communication channel between the middleware and the Elixir process. And you can use a standard input, a standard output to make this communication effectively. However, when you create the middleware, a bus appears, which is cross-compilation. Normally, NERVs handles this seamlessly, but when you are using code that is not Elixir, you have to do it yourself. So we recommend to use a well-documented library with the cross-compilation well documented to see all the process, and you can handle it by yourself. There are several wrappers for it. CMake for C projects, or NMake to handle make files that they probably not use nor are constrained with only C code. So these are the options that I will recommend to use. And for this approach, I will talk about OPC UA, which is the more complex communication protocol. They model the data of the device in an object-oriented way. So they also support secure communication. They use encryption. They have some strategies to handle this feature. We also have the public subscription behavior with monitored items. So they have a lot of features. However, it is really complicated to implement it fully in Elixir, and has very complex configuration process. So let me continue. For this approach, we select Open62541, which is a library writing on C. We select this library because it has a lot of activity in GitHub and has consolidated maintainers such as universities, such as companies that really invest on this library. So we have the security that this project will not be dead by the end of the year. So we create the middleware, and we develop this library, which we call OPEX62541. Has the following features. We also can be the server and the client of this protocol. We also available the secure communication. And here is the demo that I'm going to show you, which is we named it Denom as demonstration of Elixir nerves and Modbus communication, and that's the thing. This is the setup. The flux capacitor that I was talking at the beginning will be simulated by a Raspberry Pi. It will has two servers, one Modbus TCP server and the other OPC UA server. Both of them has two independent variables, and I will connect later an Arduino Nano just to simulate the physical environment, and this and this device will override some variables of the server. And the PLC will be emulated by my computer with graphic interface that I would like to share in a couple of minutes, but it will be complicated. But yeah, I will connect the Raspberry Pi through Ethernet, and the communication will be done. However, since I am quite of awkward position, so I will continue the presentation, and at the end we will show this demo. Available options. We also developed AVEX, which is a library to access the information of Rockwell's PLC, Rockwell's or Allen Bradley PLCs. There is another package we call SnapX to access data from Siemens PLCs. There is a third-party open source project which is called Scrub for Very Possible, and helps you implement or read data from an Ethernet IP protocol. And future work, we are eager to implement the CAN bus for our device, and the protocols that we are looking forward are CANopen and J1939, which CAN is really interesting because it's highly applicable, implementable in Linux environments and industrial in industrial environments. A special thanks, well, the whole ecosystem. I thank to all of them, the community, and our sponsors, which is my company that I'm working, and ElixirConf for make this trip possible. And yeah, this is the presentation. Now we are going to make the demo. So I am going to create my terminal and stop sharing the this screen. Okay. Oh, some updates. It's kind of awkward doing this, but yeah. Here, first we have to ping the device. So, oops, there is the history. Ping nerves. Look. So as you can see, there is no connection because I am not connected physically. So I'm going to connect the Ethernet right now. And here we go. So we can SSH now the device, SSH. And here is our terminal. We have to attach the logger to see real-time data. And here we go. Now I'm creating the Modbus client, which appears right on my other screen. And here is the, oh, let me first set up this offline Binam. This is the graphical interface for as a client. Here is going to be the logs that the device is writing on. So something that I don't tell you is that I point this value. This register will be some variable that is living in the device. So here, if I transmit the data, it appears there are zeros, right? Because there is no Arduino connected. But if I connect the Arduino right at this moment, and I don't make any short circuits, so here I can transmit the data one again, and here is the data. And here in the logs is showing the whole transaction. And I believe I can see very well, but this data right here is the one that we are sharing here, if I'm not wrong. Yeah. So this is the communication. I will disconnect the Arduino just to change the way that I'm going to use. Now I will use the function of write a coil. I will expose. I am exposing a variable which is a Boolean one, and here I can send if I want to turn on or turn off the variable. Here in the device, I show if I turn it on, it's on or off. Well, I don't grab it. Okay. I have to change the register. The register is number 1. So now the DeLorean has a start, I think. So if I turn it off, the device will stop. I think I have a typo there, but basically the logic is that if the DeLorean is already stopped, we don't have to turn it off again. But if we turn it on, the device will turn on. And this is basically a communication between Modbus TCP client and a server. Now I will share with you the other communication protocol, which is OPC UA. I am using a software which is UA Expert, which appears in my other screen. Here I can add all the exposed yes, none, yes, and here I need to connect to my device. And here, as I said before, OPC UA supports a way of modeling the device as an object-oriented way. And we have the 2 variables that I just described here. So you have to just add these variables here, and they are real-time transferring the data. So as you can see, they're increasing the data, and some of them are stopped because it is no Arduino connected. But if I connect it right now, This data should be updating now. So basically, this is the idea. I also exposed the code of the full code of this implementation in my GitHub. So if you have any doubts, you could reach me out in that channel or in the Slack channel as Aldebaran. And that's the thing. So thank you very much for hearing this presentation.